Great to be here again at Scalar. And today I'm presenting to you about some insights about the multi-threading in the Scala Native, because that was one of those features that were actually requested for quite a long time. And we really wanted to have it, so we can do the same stuff like on the JVM. So quick info about me. I'm working the Scala compiler team at Virtus Lab. I'm currently also the lead of the Scala Native team. That's not a big group, but there's more than only me working this project. And in the meantime, also doing some other stuff related to making sure that we don't break your Scala code. And let's start with some goals that we had for the multi-threading. So actually, we wanted to have most of the Java Threads API and build later upon of it. So this means that also we wanted to have mostly compliant JVM semantics, mostly because if you are migrating some code or would like to cross-compile, which is also the other point between the JVM projects, you would like to keep the same semantics. You want to keep the same invariants about how your code is going to be executed, which is not always that obvious and not easy. And to make actually usage of all of that we needed to provide you with the set of additional tools. So the futures, execution context, all the goodies that you use on the JVM, and from the Java world, because also Java did concurrent stuff. And it actually took us a while, because the very first commits were somewhere in the August 2021. At that point, I was still in the Scala Center as a member from Virtus Lab. That at that point, we were mostly focusing on adding Scala 3 support. But I made some experiments at that point. Unfortunately, soon the founding was finished, so I couldn't spend most of my time to work on Scala Native. And most of the development needed to be stopped or limited to mostly a contribution in free time. However, September 2022, at the time, Martin Anderski announced that he'd like to also contribute to Scala Native. He has some ideas for his Caprese project. And in collaboration with him, we have restored the funding, and the actual work on the multi-threading started. And last year ago, when I was here, standing on this same stage, I was saying that it's almost here. We just need a few more patches and a few more improvements, and it's ready to be used. But yeah, it's only going to be released. Right now, we currently have the Scala Native 0.50 release candidates, and they should have a final release next week. And these new minor versions brings not only multi-threading, but also lots of other goodies. For example, this initial support for 32-bit architectures, and there will be, I guess, a very good example of this in the Jakub Kozłowski's talk later today, where he would show you some very nice things that he done with it. We also had some source-level debugging support, so you can actually see what's happening in your code. We've prepared for the new SIPs, like changes to the Scala 2 standard library, or added some additional layers that would allow to enrich the Scala Native ecosystem, and for example, using the Java service providers, which we would like, for example, to implement based on them, for example, parts of the Java security or maybe custom char sets or whatever would be needed. Last but not least, we also have these now, the continuations primitives. These were designed by Nguyen, who has later a talk after this the next break, and he would show you some more insights of, hopefully maybe some insight how they might be used in the Gears project. Because these are powering their version for the Scala Native. But in general, there was a lot of changes in the meantime. Lots of code has done. And from this stage, I would really like to thank for all the contributors that actually spend their free time, to help to improve Scala Native, its ecosystem, and to make it work. So I said that multi-threading is coming. So what is working already? So from your perspective, most of the stuff, futures, tasks, execution context, Synchronized blocks, whatever we need to work with concurrency is already there. When it comes to Java concurrent, we have most of the stuff. There's like 90 classes, utilities, that are defined in there. We currently have ported around 70 of these, and the remaining one will be added soon. All of that was possible mostly because Java concurrent stuff from the JSR 166 was published to the domain with a and we could have just to the public domain, and we could have just mostly use it and adapt it to our needs. And to some extent, Scala did it at the point of Scala 2.11, where we had our own foraging pool, for example. But why have it took that long? I mean, just creating a very simple threads wasn't a problem. You can use like POSIX threads or Windows native threads, put them into some class, some container, and run execution, right? Yeah. Actually, in practice, there's a lot of more things to consider. And when you start to actually play with it, when you try to combine some things, we get into problems. We need somehow to have a thread-safe lazy vals. So it needs to have a thread-safe initialization of some objects. Again, object monitors, mentioned in the previous talk. But also a lot of other stuff that needs to be considered, it needs to be adapted. Also, the code base needed to change sometimes a bit. So all of this took a while. And from my perspective, the biggest issue was the garbage collector. The one thing that writing code we typically forget about, sometimes we come back to garbage collection, we get problems with performance, of course, because then we remember again that we have some stubs, some additional overhead needed to get our memory back for our usage. But when writing code, we don't really we don't really take care of it too often. And garbage collector has two main jobs: how to allocate new objects, how to reclaim no longer unused memory. That's all. Two main jobs. What can go wrong in here, right? So for the first part, actually, we had a quite good design in the garbage collector itself, because we could treat a garbage collector's heap in the Emix, the default garbage collector of the Scala Native, as a one continuous range of memory, which is separated into a so-called blocks. Each block is around 32 kilobytes of memory, and they are tended to just help us with the performance overall. We don't allocate objects directly on the heap. We use blocks for that. And so we have the thread local allocator on the very bottom of the screen that actually creates space for new objects based on the blocks that we provided to him by the global block allocator. So in this case, because we had this very good separation, we could just synchronize only the block allocator, and then thread local allocators, which do not share any state, didn't require any synchronization, so they could be really fast. And the only need for locking or whatever would be needed only when they would run off the available blocks. But there is other problem: how to reclaim memory. And again, quick summary of GC works. In our case, Emix is using the mark and sweep algorithm. It means that it runs two phases. In first, it marks all the objects that are alive, and in the sweep phase, it removes all the memory, reclaims all the memory from the objects that are no longer reachable. But how do we actually know which objects are reachable and which are not? For this, we need to have the concept of root objects. These are objects that can be found in some well-defined places. This might be, for example, local variables on the stack of a thread, registers, because references to objects might be passed to function calls in our registers. Later, this might be some global objects or some custom areas that were hinted by the users. So when we have actually this set of objects that we know that are used, that needs to be kept alive, we can just see which other objects they reference in the heap, and we can then mark them. And when we do it, we would also do it recursively until we would visit all the alive objects, and we can create this directed graph of dependencies. So then in later stages, we can just sweep everything that is not used. But there's one problem, because in single-threaded code, it was quite easy. You needed to bother about data races. But let's assume that at this point where we are doing this marking phase, some other thread wants to allocate new object. So if it might happen that it would get the new object, it would remember the reference to it, but the object itself was not marked. So it'd be swept again. And if that happens, other thread, or in the same thread, might overwrite the same memory location with some other data. And this quickly leads to some runtime failures, segmentation faults, etc. We don't really want that. So how do we deal with that? The simplest solution that exists both in the JVM and the Scala Native is to stop the word. And that simply means that we want to achieve a state in which we know that no user thread can allocate new objects or might require us to be somehow involved in the garbage collection. So for example, we can introduce some concept of stopping the threads and later resuming them after we would finish garbage collection. But how do you actually can achieve something like that? After all, you might be executing something that should remain atomic, or you might maybe lose some references. It depends. Here we typically have two kinds of them. Like for the languages that are not managed or more like low level, like C, which can use garbage collection, but typically tend to not use it. For example, using BOEM implementation of the garbage collector, they might prepare signal handlers, dedicated signal handlers, and send some well-known signal to each thread, which would then yield the current execution and would interrupt it, which would force it to execute the installed signal handler. The main problem with this is that if the function we're calling is, for example, waiting on a socket, and this is a blocking operation, the call would fail. We would get some information, indication that in the error variable that it failed by being interrupted, but it actually requires you to repeat your operation. So in that case, it's not a very good fit for high-level languages like Scala, where we don't want to bother too much about this low-level stuff. That's why languages like JVM, .NET, and Scala Native as well uses a so-called cooperative suspending of the threads. This means that not the GC controls when you stop your execution of the thread, but rather indicates that thread should be stopped. The thread itself is required to check at some cyclic operations, for example, occurrences, that it actually should be stopped. This is actually called maybe just treated as a simple polling of the GC for some flag, for example. And it gives us much more control on when you would stop the thread and would yield the execution to the garbage collector. So you can be sure that we actually are stopping execution at some well-defined point, which is safe. So the very simplest way of having these yield points, which would be typically injected by by a runtime or by the code generation when compiling the code, would be to just have some simple Boolean flag and work accordingly. But we can do better. Let's remember that these yield points are inserted in lots of functions. Basically, every function we would have typically would have at least one yield point. Or for example, we would insert them when coming back from the function, or when repeating some loop. So we should make sure that they are as efficient as possible. And in fact, that's not the best, that's not the peak performance that we can get by pass checking the Boolean flag, because we are actually creating branches of our code. At a very low level, there is the creating a branch, some jump or some ways of control, is a bit slower than executing instructions one by one. And some optimizers actually, when dealing with numerical operations with your logic, can rewrite these jumps, if statements, with some branchless variants of a code. And for the Scala Native and for the yield points, we can use another technique to actually make it branchless. It was described in one of the papers shown below. And you might be wondering why there is no call to any function. There is just a read from some variable. Actually, this is a kind of special variable because it might, at some circumstances, trigger segmentation fault. This GC yield point, or rather it should be called GC yield point trap, is an address to some location in a dedicated page of memory to which you can control the access. So we can, for example, revoke access to writing or reading from these locations. And if you would try to do it, the system would trigger the controlled segmentation fault, and then we can just use our own signal handler to then work on it accordingly. And when it's done, it would come back again to executing normal code. This allows, for example, us to have no to very limited amount of overhead, which is typically just a one single instruction. So it's, even though it might not seem like a big difference, it is, because it's run millions of times. However, we've talked about yield points. And what, for example, if to stop the thread, we need to get the yield point, right? But what if there is some occurrence that blocks us for that? For example, you might be running the lock on a mutex, that is a blocking operation. And let's say that at the same time, GC wants to start the collection. At the same time, the owner of the mutex might be already stopped. And this would, in result, because it would wait for the other threads, we get deadlock, even though it might be really unexpected in here. So how can we deal with it? One solution would be to just maybe annotate that we are entering some range of addresses, some range of the code, and that tells that it would not have any allocations. And basically, that's what the JVM and the Scala Native does, is that before having a call to the external function, it would send a notification to the GC. Hey, I'm now entering this unmanaged code. I won't allocate anything, so don't wait for me. And thanks to that, garbage collection would skip waiting for this thread. However, there might be a requirement to have some more information. For example, we've seen before that we require the registers of the thread to scan it for the references. So changing the state would also make, for example, dump of these register values, so we can scan them later, or, for example, make some other operations. And this introduces some kind of overhead. It might not be big, but again, it's accumulating over the time, right? So we, of course, don't want you to write code like this. You would forget about it, and I would definitely as well. So instead, in the new Scala Native, there is like a dedicated annotation for the external functions, so that if we know that we got some functions that can block for infinite amount of time, or for the long amount of time, they would use this notification system for the GC to inform it about entering the unmanaged part of the code. And this would happen automatically. Of course, we can also enable it globally for all the functions, and that's the semantics of the JVM. Because on JVM, we don't call external functions very often, unless we're working a lot with the GNI. But again, as we know, GNI has its own overheads, and that might be one of the reasons why. Okay, and as we are now ending the part about the garbage collections, well, I have a great recommendation. If anybody would like to learn more how GCR are working, there is a book. Richard Jones is one of the co-authors of it, which is a very heavy lecture, like I think 1,000 pages at least, that describes many different garbage collections, algorithms used under the hood, and different ways of dealing with garbage collection. And it's a very good lecture. However, even if you would understand all of it, there's still debugging of the garbage collection. And that's not a good experience. I can go into it. One thing that I actually was dealing not so long ago was catching one bug for a week. And maybe somebody would do it quicker, but I'm not that good developer, probably. Anyway, let's go to the next topic, object monitors. You've learned about object monitors in the previous talk, so you now already probably should know how they might work on the hood. But in my opinion, JVM or the Java had one big flaw in the design. The fact that you can synchronize on any ordinary object. You can create an anonymous one, and it would be forced to also have some overhead. Because if you want to synchronize, you need to remember about the state of this monitor, about this log. So in fact, all the objects, or rather layouts of the objects on the JVM, and unfortunately currently also on the Scala Native, need to not only keep the information about the runtime information of the given class object, but also the additional monitor information. And this might, of course, have underneath not only like information about the owner, maybe a recursion counter, because we can get nested entries to the object monitor, so we need to track them as well, but also like another information that would be required to implement wait and notify instructions. But even if you would not allocate this object monitor by default, we still can waste lots of resources. As you might know, now synchronized logs are not recommended for the use, especially in terms of the virtual threads. And there's a lot of code that, for example, might enter the synchronized block once, and the object would live for a very long time. So there's still, like, at least in this case, at least 100 bytes that would be allocated unnecessarily for the given object, for the whole lifetime of it. But we can do better, and we can use one trick. So there is a technique of the so-called finlogs. The finlogs are actually treating the variable for the monitor not only like a reference to this heavyweight object, but also like a bit set. So for example, you can, initially the object monitor is in the fin state. In this case, we treat it as a set of bit fields on which we can operate with some bitwise operations. And then you can, for example, get the really required information that is needed as long as there is no concurrent access to this object. As soon as because we would modify the state of this monitor by using concurrent set operations. And as soon as this operation fails, it means that some other thread tried to do it as well. So in this case, it would wait, it would spin loop until it gains the ownership, and then it would inflate the object to the actual heavyweight implementation, having the full implementation of wait and notify methods and all this heavy machinery under the hood. But wait a minute. If I can treat it either as a bit set or as a reference, I can mess things up, because I can think that it is an address, but it's still, for example, some random number somewhere in these bytes that we interpret as address, And loading from that would lead to segmentation fault, because it's an invalid address. So we need to know at which state we are. But we don't want to create additional field for that. And especially in terms when you get to the inflated version of the monitor, in which we want to have the exact address. So we need all the information that is required to get us to this single object. And there is one nice trick for this, because when you allocate stuff, it is typically 8 bytes aligned. And that means that the free least significant bits can store any kind of information that you can store in the free bits. And when you want to get the original reference, you can just apply the mask and get the original value. And that's the other trick that is used by both JVM, by the Scala Native, to actually make it happen, to make the synchronized blocks as lean as possible, and make them go fast and efficiently. Actually, right now, I had a few more slides, but I thought I wouldn't be able to talk about them. I finished sooner than I expected. So we can get some questions from you, and thank you for coming to my talk.